Yeah, this is my first AutoSense. I've really been enjoying getting to see a lot of customers that I work with regularly and hearing about new innovations in the industry. The biggest architectural change that we see is the move away from loosely coupled domain-specific ECUs and into tightly integrated deterministic compute fabrics. And what I mean by that kind of breaks down into three different areas. The first being synchronicity between all the sensing pipelines needs to be paramount. So radar sensors, camera sensors, LiDAR sensors, they need to be tightly temporally coupled, often within milliseconds or even sub-millisecond ranges, so that the vehicle can receive all the information it needs to paint a coherent picture of its environment. Secondly, I would say would be hardware accelerated processing and networking. Oftentimes the data that we're getting from these various sensors requires specific application processing, and the way forward for that, I think, is fixed function DSPs, or digital signal processors, that allow you to ingest a lot of raw data and make decisions very quickly. And then lastly is functional safety. As cars get more autonomous, they take more responsibility away from the driver and onto itself. So achieving ASIL D as in Delta is now paramount. Innovations in centralized compute and zonal architecture are very exciting, and it does shift the risk profile that automakers and tier ones need to be aware of. Single point failure model versus the robustness that comes with distributed processing. In the past, if your car lost a motor system or a lighting system, that didn't mean that you lost your powertrain, right? But if you're condensing everything down to a single compute unit and then you lose that, the blast radius, so to speak, of that failure is much larger, meaning that design redundancy for things like additional SoCs in case of failure, additional power trees, doubling up on the cabling going to each sensor in case you have a physical failure are going to be paramount moving forward. Secondly is the over-the-air update, or OTA. That's a big target for a lot of these automakers, being able to push out new features, new functionality via software updates. That will be driven by this zonal architecture, but one thing to keep in mind is that also does open you up to the challenges of software-defined vehicles, primarily meaning things like cybersecurity. Now that you're sending data in and out of that car regularly, you need to make sure that that's protected. Also things like revision control and trying to maintain these designs across varieties of hardwares, car lineups, that sort of thing. These tier ones and automakers have spent decades perfecting their craft with domain-specific ECUs and software. So moving from a company that knows how to do one thing really well and trying to pull all that information into a single compute unit requires that the integrators there be able to maintain OSs, middleware, application-specific hardware, update softwares, all the above, which that skill set can be quite rare and possibly costly. And honestly, for automakers, I would recommend, in order to get past this and get something back out of it, is to treat their compute and networking backbones like investment platforms. What I mean by that is design your car for probably about a 10-year life cycle, and as opposed to doing hardware revisions every step of the way, you're able to now pump out new functionality, new features, and upgrade the experience through software, service lifetime, that sort of thing. The move from things like slower CAN or LIN interfaces to Ethernet, or possibly FPD-Link for serialized communication, is not just about bandwidth, but it's about upgrading the capabilities of your entire architecture. Firstly, that means that you're able to now ingest raw data from these sensors, whereas pre-processing at the edge was kind of the norm. Being able to send high payloads of raw radar, camera, or maybe even in the future LiDAR data to your central compute gives you a lot more flexibility. And then lastly, the biggest thing is that it just enables a lot more data to go to and from this vehicle. Kind of far into the future, not so far anymore, but we are looking at integrating things like high definition maps, infrastructure information, and then even things like vehicle-to-vehicle communication. So if you could picture I drive vehicle A, let's say, and a mile up the road is somebody else who also drives vehicle A, if they see an object on the road, then now we're talking about that information being sent to that manufacturer and then sent back to me in order to paint that picture of the road ahead of me in much more vivid detail and in real time. That will help us address things like fallen trees, construction zones, things that you can't plan for on a regular basis. Yeah, so sensor fusion is definitely one of the most exciting, but also one of the most challenging areas in ADAS right now. One of the big gaps is sensor degradation. Every sensor has its own pros and cons. So for automakers and designers, being able to incorporate the multi-variables that go into play with all these different sensors in real-world scenarios is kind of an open gap, I would say, right now. Secondly is producing edge AI at scale. It's hard enough already to train these perception models, but to roll them out across a variety of hardware configurations, sensor degradations, and even regional regulatory environments makes that challenge just all the more harder. And then lastly is the gap between perceiving and understanding. When you're driving as a person and you see somebody on a bike coming towards a red light, you might very well think that person is about to blow through that red light. That understanding is the difference between a safe vehicle and one that can only see an object, right? To get past these gaps, we're going to see a standardization in sensor interfaces, open data sets for common edge cases for safety purposes. And then lastly is that tier ones and OEMs are going to work directly with silicon providers such as Texas Instruments in order to optimize their systems and architectures to reach these L2 and L3 goals rapidly and always have the best features available.